Okay, good evening dear students, and today we are going to talk about the topic written on the board, propped cantilever beam with an inbuilt hinge, internal hinge. I am S.K. Sharma from ITBHO and IIT Roorkee. Students normally, one of the biggest problems that they face in shear force diagrams and bending moment diagrams problems is when an internal hinge, a hinge is introduced within the beam. You must have solved hinge as a support. But once hinge comes in between, many of us feel a bit threatened, or many of us feel that we may not be able to solve it because it gives us an additional equation. So what we need to do is, for example, we are just taking a very simple case. There is a UDL of 1 kilonewton per meter, and there is a concentrated load here, and this is a total of 15 meters of beam. This is a propped cantilever. Propped cantilever, as you may be aware, is basically a cantilever here, and it is propped here. But once you have a cantilever here, you have basically 3 unknown reactions and 3 equations of statics, and one more unknown here. It becomes a statically indeterminate problem. But the moment you introduce the hinge, it gives you additional equation. So this additional equation will help us make it a determinate structure. Now, for the purpose of solving, we shall break this big problem into 2 parts. Number 1, we'll take this 10 meter part of the beam separately. We'll take this 5 meter part of the beam separately. बीच में जहाँ ये hinge है, hinge will divide this beam into 2 portions, not just mechanically but also by the action that hinge is introducing at this beam part. Let me just tell you how. For example, if we are joining 2 parts of the beam at a hinge, then possible actions are here. It does not resist a moment. But what it does, it resists a shear force. For example, if you want to just take it away, it will not move. What is shear force? Shear force is something like this. If this beam part, you consider shear force is something like this. The 2 beam parts joined as a hinge is just like a door where you move like that, a hinge here. And as I said, it passes a moment, it does not resist a moment, but it resists a shear. For example, if you just want to cut it by a shear force, just want to move it down by shear force, this hinge is going to resist. So the action, the mechanics action that this hinge is permitting is something like this. Now you have a cantilever support here, and you have a roller support here, and this does not move down. It can only just twist like that, passing a moment. It will not resist a moment. So ultimately, in fact, the bending moment value at this point is going to be 0. That's just a foregone conclusion. But how do we analyze this beam? Some simple techniques are used. For example, you just break this particular beam into 2 portions. 2 भागों में इसको बांटना है. One is this, another is this. Now this we have a roller support here, so it gives an upward reaction. And in this portion, as I said, this does not allow the beam to go down. So this load, which is in the middle of the beam, is being resisted by this hinge here. So there is when it is not allowing the beam to go down, there have to be an upward reaction here. जैसे ही upward reaction होगी, this particular part of the beam is going to act as a simply supported beam. So this particular portion we see solved as a simply supported case, which then becomes a very simple case. And this particular portion, for example, this portion is not being allowed to go down. So whenever there is a resistance to movement, there will be reaction. Whenever there is a resistance to movement, I repeat, there will be reaction. So if there is a reaction here by this part of the beam on this in the upward direction, again by Newton's third law, this part of the beam will again put a force in that direction on this part of the beam. So you have this force, same force as on this part of the beam, reaction from this part of the beam on this part of the beam through the hinge is 10 kilonewtons upward, and by the Newton's third law, you will have a reaction of the same magnitude coming down here. And rest of the beam, you already have a UDL. So this bigger problem gets resolved into 2 parts. One of that is a simply supported beam having a load in the middle and supports at the 2 ends, and second, a concentrated load at one end, and then a UDL. Now how do you solve it? This bigger problem now gets resolved into 2 smaller problems: simply supported beam and beam with a UDL. Beam with the UDL, case given as 10 meters, and this is beam with a simple supports is 5 meters long. So once we resolve it, you have reactions 10 kilonewton, very easy to calculate thereafter. You must have done it hundreds of times. A simply supported beam with concentrated load in the middle has reaction, half reactions of the total load on both of the sides. So you have a very simple case here, and a concentrated load as a reaction to this, a concentrated load here, and then a UDL. So broken into two simple cases, a simply supported beam and a cantilever with a UDL and a concentrated load. So how do we go ahead? So again, as I said, break this big problem into two smaller problems. We have already done so far as the load diagram is concerned. Now we do the same thing so far as the shear force diagram is concerned. When we draw the shear force, we draw shear force separately for this part of the beam and separately for this part of the beam. Again, BMD, we draw separately for this part of the beam and again for this part of the beam, and ultimately we join them together. After 5 meters and after 10 meters we join them together, and same for BMD. Now, you have a 10 kilonewtons. So far as if we consider this beam and try to draw a shear force diagram, you have the 10 kilonewton going upwards. So if we take any section, for example, if we take a section here at a distance x from the right reaction, then, and if we consider the loads to the right of the section, then the right portion is going up. Now, the convention, normal convention that we follow in drawing the shear force diagrams, the bending moment diagram is like this. If the left portion, left of the section is going up and portion of the beam to the right of the section is going down, then this is considered to be a positive shear force. And similarly, if portion to the left of the section is going down and to the right is going up, is considered to be a negative shear force. You have a liberty to take the other type of a sign convention for so far as shear force diagram is concerned, but this is followed in the most of the books. It doesn't matter if you take this to be negative, this to be positive, it doesn't matter, but the only thing is that you need to just specify here. For bending moment, you have basically a sagging moment. If the beam is sagging like that, that's considered to be positive, and the beam is hogging like that, that happens in a cantilever, you consider that to be negative. So by this sign convention, we go. For example, if the portion of the beam to the right of the section, it is going up, then this, by this sign convention, is basically negative shear force. So starting from here until here, you have 10 kilonewton of negative shear force. As soon as you come here, there is a force downwards, and again if you take a section here and consider part of the beam to the right of the section, then you have 10 kilonewtons upwards and 20 kilonewtons downwards. So that is 10 kilonewtons downwards if to the right of section. Then if the beam is going down, then this is going to be positive shear force. So from this point onwards, it's positive shear force of 10 kilonewton. And thereafter, once you come here, okay, as I said, we stop the analysis and look at this portion separately. You have a 10 kilonewton force, concentrated load here, and you have a basically UDL. So once you draw its shear force, 10 kilonewtons effect will be some sort of a rectangle, and the effect of 1 kilonewton per meter, a UDL, on a cantilever shear force diagram will be some sort of a triangle. If the rectangle and the triangle join together, that's for some sort of a trapezoid. So in this case, the cantilever portion, for example, this is what I was saying, this portion coming from here is a continuous rectangle effect of this load here, and thereafter the UDL triangle, total you have a trapezoidal shear force diagram on to the basically left of this hinge. When we were talking about the bending moment diagram, we had this triangular portion, basically a triangle like this, value rising from 0 to 25 kilonewton meter at this place, going to 0 again. And this particular part of the BMD came from this particular part of the beam. Once we consider this particular part of the beam, we have a different bending moment diagram coming for us, and you can just appreciate for this part of the beam, it will be a sagging bending moment, You see, this is producing a sagging moment here, this is producing a sagging moment here. We also need to, while talking about mechanics, we need to also visualize as to what is happening on the beam. So once you visualize, there is a sagging moment, giving a positive bending moment, and this cantilever, a very well known case, a cantilever loaded and producing a hogging moment here, negative here. So from this portion to this portion is going to be negative values. So how do we calculate which values are going to be there? The curve has to be parabolic, which is is very clear because it is a UDL, and the UDL gives a loading of WL square by 2, where W is basically the load per unit land, which in this case is 1 km/meter, and L is the land. So in this case, this UDL is going to give you WL square by 2, that is W is 1, L is 10, 10 square is 100, 100 by 2 is 50. It's going to give a load of 50 kN here, and additionally, you see this total is 150. Where the other 100 come from? Other 100 has come from this particular portion, 10, and this distance is 10. So 10 into 10, 100 kN/meter. And you see, this cantilever is here, and this will attempt to take it down here, make it a hogging case. Hogging means negative, and as I said, the equation is parabolic. So negative bending moment, 10 into 10 coming 100 from this, and WL square by 2, 50 coming from total of 150 kN/meter of bending moment coming from this. So you have parabolic curve here. You join the two, you get the bending moment diagram. You join the two here, you have got the assembly diagram, and the loading diagram again was a combination of the two. So fine, this is just the explanation. How do you attempt to solve a complex problem by breaking that into two portions? Thank you very much. This was Professor S. K. Sharma. You are welcome to tune again.